So I'd like to start by thanking the organizers for putting together this wonderful event and for inviting me to speak here. And then, of course, I'd like to thank Nati for many, many different things, mostly for teaching me a huge part of what I know about quantum field theory and string theory, and for always supporting me and my career ever since he called me at my student office in Tel Aviv University and offered me a postdoc position before I even applied for it. So thank you very much. And I'd also like to thank Nati for teaching me more specific things. So I'd like to thank Nati for teaching me to always question all assumptions, to be rigorous wherever possible, and not to settle for incomplete understanding, because many times if we don't do that, we miss important things. Another very useful lesson that I learned from Nati is that the more references you put in your papers, the more people will complain. So that's a very useful lesson that I've tried to implement. One thing that Nati's tried to teach me many times but has not succeeded is that you should publish only what you understand and not what you don't understand. So I guess it was obvious already in this conference that some of Nati's disciples have managed to learn that and other ones have not. And I'm definitely in the not one of the people who have not taken this advice. On a more personal level, I'd like to thank Nati for his direct, no bullshit style. I know that I've heard from many people that they find this style intimidating, but I never found Nati intimidating. And well, I think generally speaking, Israelis are familiar with that style, so they don't find it intimidating, while people of other nationalities it takes them time to get used to it. And last but not least, I'd like to thank Nati for all of his contributions to quantum field theory and string theory that have shaped most of my research in the last 22 years. It took me a while to figure out what I should talk about at this conference. One obvious choice would have been to talk about my projects with Nati. We've had many collaborations that I've found very enjoyable and educational. I was proud to see that I am in the top 10 of Nati's collaborators, all of which are speaking here, by the way. And again, we've had many different collaborations that have taken any time between 2 days and another one that's 3 years and still running. And so I could have talked about these projects, but if I would have done that, I would have been forced to talk about things that I don't understand. And as I said, Nati would not approve of that. But still, it was tempting to talk about them, especially following the saying that's attributed to Enrico Fermi, that you should never underestimate the joy people derive from hearing something that they already know. And of course, at least one of the purposes of this conference is to give Nati joy. So I could have done that, but in the end, I decided against it. Well, partly because of this reason that Nati would have been shocked if I would have said things that I don't understand about our joint projects. And also because I think that even though Nati is very focused, he does still enjoy also hearing things that he doesn't know about, at least for a few minutes. So what I'll do today is actually the opposite. I'd like to talk about 3 topics that Nati has not yet worked on. And one reason for doing that is that Nati likes every 2 or 3 years to completely change the topics that he's working on and to work on completely new topics. So maybe these topics could be some possible suggestions that you may want to work on in the next 60 years. So my talk will be composed of 3 parts that are completely independent from each other, and their only common feature is that all 3 of them are topics that Nati has not yet worked on. So I know that this goes against the spirit of the other speakers, but anyway. So the first topic I'd like to talk about is theories with a number of supercharges that is not a power of 2. So before I prepared this talk, I was sure that Nati has worked on any possible number of supersymmetries in any possible number of dimensions and has made seminal contributions to all of them. But I was surprised to discover that that's actually not true, and that at least since 1987, I'm sure Nati will correct me if this is wrong, as always, but at least since 1987, I think Nati has not done any work on theories whose number of supersymmetries is not a power of 2. Even though there are interesting examples, in particular above 2 dimensions, there are the 3-dimensional n equals 3, 5, and 6 theories, which have interesting superconformal examples. And there's the 4-dimensional n equals 3 algebra. So today I'd like to focus on 4-dimensional theories with n equals 3 superconformal symmetry. The reason that I'm interested in these theories is that n equals 4 theories in 4 dimensions are essentially classified. We believe that they're in one-to-one correspondence with the Lie algebras, although we don't yet know how to prove that. For n equals 2 theories, there's been much progress in finding large classes of these theories, mostly by people in this audience, but I think we're still, at least it seems that we're still far from a complete classification. So it seems natural to discuss this intermediate case of n equals 3 because, well, certainly if we can't classify n equals 3 theories, we have no chance of classifying n equals 2 theories. When you start thinking about n equals 3 theories, you immediately run into the problem that when you look at the representations, then the only free multiplet of n equals 3 supersymmetry is identical to the n equals 4 vector multiplet. It has a vector field, fermions, and 6 scalars. And also the only interactions you can add to that multiplet that preserve even just n equals 2 supersymmetry are the usual interactions that we have in n equals 4 super-Yang-Mills theory. So that means that if you want to discuss just pure n equals 3 theories that don't have an enhanced n equals 4 supersymmetry, then there are no free theories of this type and also no weakly coupled theories of this type. So perturbation theory is useless for studying these theories. But we still want to learn about them. So what can we still say about these theories? One thing that we can say just from this analysis of free multiplets is that if you have an n equals 3 theory, then if it has a moduli space where it flows to some free theory, then that free theory has to involve R free vector multiplets in the infrared so that the moduli space is some 6 R-dimensional Coulomb branch, just like in n equals 4 theories, but that has to be true also in n equals 3 theories. So about a year ago, we started looking at some general properties of pure n equals 3 theories that we can derive just from their superconformal algebra. One property that also Ken and his collaborators found in parallel and that Ken mentioned yesterday is that n equals 3 theories do not have any exactly marginal deformations that preserve supersymmetry. In fact, they don't have any marginal deformations preserving supersymmetry. That's not too surprising since we already saw that they don't have any weak coupling limit, but they also just don't have any marginal deformations, and they also don't have any relevant deformations that preserve n equals 3. They can have relevant deformations that preserve n equals 2 supersymmetry, but not the full n equals 3. Another property one can show is that they don't have any global symmetries beyond the R symmetry, which is SU3R cross U1R. And again, that's similar to n equals 4 theories. And also, if you study their superconformal anomalies, you can prove that the two independent anomalies, A and C, have to be equal to each other. And again, that's similar to n equals 4 theories, but not like general n equals 2 theories. So, so most of these properties are similar to n equals 4 theories, so you may think that maybe there aren't any pure n equals 3 theories, that they all have n equals 4, and indeed we tried to prove that for a while and did not succeed. And indeed, earlier this year, Garcia, Echevarrio, and Regalado found the first examples of pure n equals 3 theories that don't have n equals 4 supersymmetry. To understand their construction, we can start from M theory on C4 mod zk, where the zk acts equally on the 4 complex coordinates. That preserves exactly 12 supercharges, in this case, three-dimensional n equals 6 supersymmetry. And if you put n M2 branes on top of that, then you find an interesting class of three-dimensional n equals 6 superconformal field theories. For the special case of k equals 2, then this is just an orientifold that preserves three-dimensional n equals 8. Now you can take one of these complex planes and replace it by a torus. So to study C3 cross T2 mod zk, and you can do that if that torus has a zk rotational symmetry. So for k equals 2, that's true for any torus, but for k equals 3, 4, or 6, you can find specific complex structures where there's also such a symmetry. For instance, a square torus has a Z4 rotational symmetry. So in those cases, you can discuss M theory on C3 cross T2 mod zk, but then you can use the duality between M theory and a torus and type 2b on a circle to lift this to F theory and discuss F theory on C3 cross T2 mod zk, where here the zk acts both geometrically on the C3 and it acts as an SL2Z duality transformation on the torus. So this preserves 4D n equals 3 supersymmetry, and you can put n D3 branes on top of that and hope that at low energies this flows to a family of 4-dimensional n equals 3 superconformal field theories. Again, for the case of k equals 2, this is just a standard orientifold plane in type 2b string theory, and that preserves more supersymmetry. While for other values of k, you divide here by an S-duality identification, so these are called S-folds. So this gives us a large family of n equals 3 superconformal field theories. Naively, that family is labeled by one of these integers, 3, 4, or 6, and by n, which is the number of D3 branes that you put in. But it turns out, as I've studied with Yuji, that these theories have an extra discrete torsion parameter. For the case of k equals 2, that's the well-known fact that there are 4 different types of orientifold 3 planes in type 2b string theory. And it turns out that also for k equals 3 and 4, there are 2 different types of these S-folds. Well, for k equals 6, there's only 1 type. So there are actually 5 different classes of conformal field theories here labeled by n. Now, the theory coming from n D3 branes has a 6n dimensional Coulomb branch corresponding to moving the D3 branes around. And you can compute from this construction the dimensions of the operators whose expectation values label this Coulomb branch. In n equals 4 theories, there's also such a Coulomb branch, and in that case, the lowest dimension operator, the lowest dimension Coulomb branch operator always has dimension 2. In these theories, the dimensions are k, 2k, and so on up to n minus 1k, and then there's an extra operator of dimension n times L, which in the case of the orientifold is analogous to the Pfaffian operator that appears there. And from these dimensions, you can also compute the central charge of these theories that I did not write down. Another thing you can say about these theories, just from the construction, is that their ADS dual is F theory on ADS 5 cross S5 cross T2 mod ZK, where again the ZK acts as an S duality transformation. So this allows us to compute properties of these theories at large n. But otherwise, it's very hard to say anything about these theories because, of course, they're strongly coupled because of this S duality identification. There are some interesting special examples of these theories. The minimal example, in the sense of having the lowest central charge, is the case of n equals 1 and k equals L equals 3, where you just put one D3 brane on a Z3 singularity. In that case, the moduli space is just 6-dimensional, and there's a single Coulomb branch generator that has dimension 3. So that's, at least in this class, that's the minimal theory that has the minimal central charge. Amusingly, it turns out that if you look at the theories of 2 D3 branes, then there's a special case of L equals 1 where they happen to give theories that also have an enhanced n equals 4 supersymmetry, so that one of their multiplets actually contains an extra supercharge that enhances the supersymmetry to n equals 4. So for k equals 3, this gives you a brane construction, if you want, of the SU3 n equals 4 theory. Well, usually from brane constructions, we only get U3, but here we get SU3. For k equals 4, you get the SO5 super Young-Mills theory. And for k equals 6, it turns out that you actually get the n equals 4 theory with gauge symmetry G2. So this gives us a brane construction for this exceptional gauge group. So there are many open questions in this field. The obvious one is, can we find more examples of such pure n equals 3 theories? There are no more obvious geometrical constructions of this type, but perhaps you can do something else. One thing we're trying to do is to see if you could get these theories by deformations of n equals 1 theories, because n equals 3 theories can have exactly marginal deformations that preserve n equals 1 supersymmetry. So one can hope to find some examples in this way. And of course, you can use the conformal bootstrap methods to try to, using n equals 3 superconformal representations, to try to find more examples of this type, and in particular to see if the minimal theory that was constructed by these string theory methods is indeed the minimal n equals 3 theory, or if there are some some smaller theories in the sense of having a smaller central charge. And as I said, the big question is, can we actually classify all of the pure n equals 3 theories? And it certainly seems like this should be easier than classifying all n equals 2 theories. So I think it's, in some sense, a necessary first step. So this finishes the first part of my talk. Probably it's, well, okay, maybe we can stop for questions already now.
If you have a single brane, or U1 theories there, and n equals 3 theory?
Yeah, no, in that case, you just have a U1 theory, and that always has enhanced n equals 4. That's right. So that's a trivial case. So, okay, I guess other questions maybe we should leave to the end. Otherwise, Nati will feel obliged to ask a question about every part of the talk. And of course, he doesn't have to. So the second topic I'd like to talk about is a topic in conformal bootstrap. And again, I was surprised to see that Nati has never worked on this topic, at least since the days of two-dimensional rational conformal field theories, where the bootstrap is in some sense obvious. Again, this is a possible topic for the future. And what I say here will be based on work which is still very much in progress in collaboration with Fernando Alday and Yesavisi and Eric Perlmutter, who is here. So let me remind you what the conformal bootstrap is, in case that's necessary. So conformal field theories are labeled by a set of, or characterized by some chiral primary operators, OI of x, that have some dimensions and spins. And they have OPE coefficients, Cij, and we believe that these properties determine at least all the local properties of conformal field theories. You can look at 4-point functions of 4 different primary operators, and then you can do the OPE expansion either in the channel where you bring together O1 and O2, or in a channel where you bring together O1 and O4. And in the first case, you find an expression for the 4-point function that's a sum over all the operators appearing in this O1, O2 OPE, and it takes this form. So conformal symmetry implies that these 4-point functions are functions just of cross ratios of these 4 coordinates that I'm labeling by u and v. And then there is some specific function that's the contribution to this 4-point function from any specific operator of some dimension and spin that appears in this OP. And then the expression that you get from one channel has to be equal to the expression that you get in another channel if you just exchange these 2 cross ratios corresponding to the exchange of x2 and x4. So this is a general property. It's called the crossing equation that any conformal field theory has to satisfy. And one can hope that, well, this equation certainly gives us lots of constraints on conformal field theories, and one may hope that it would be enough in some sense to classify. Of course, this equation is not sufficient for a consistent conformal field theory. There are other conditions, but it's certainly a necessary condition for a consistent conformal field theory. And there's been lots of progress on analyzing this equation in the last few years. Now I'll talk about this equation in the holographic context. So we know that any quantum gravity theory on d plus 1 dimensional anti-de Sitter space is equivalent to a d-dimensional conformal field theory, and therefore it automatically obeys this crossing equation. And that also gives us a method to generate many solutions of this crossing equation. So if our quantum gravity theory happens to be weakly coupled, so in particular the ADS space has to be much bigger than the Planck scale, then we can just compute correlation functions in the CFT perturbatively by putting in sources at the boundary for this quantum gravity theory, and then we can expand them in Feynman-Witten diagrams. So the first contribution to a 4-point function of identical operators comes from a disconnected diagram of this type, where these lines are propagators of the field dual to this operator in anti-de Sitter space. Then at the next order, you can have tree-level diagrams like this, and then loop diagrams, and so on. And of course, the full sum of these diagrams by construction has to give you a solution to the crossing equations. And weakly coupled gravity theories of this type are dual to a class of CFTs that I'll call large N CFTs because, well, large N CFT is always in this class, although there are also other theories that don't come from gauge theories. So in weakly coupled theories, there's a well-defined distinction between single particle states, 2 particle states, 3 particle states, and so on. And these are dual by the ADA CFT correspondence to single trace operators with a dimension related to the mass of the corresponding particle, and then you have double trace operators, triple trace operators, and so on. In this context, the OPE coefficient between 3 single trace operators translates into a 3-point coupling in the bulk, and the theory is weakly coupled, so that's a small parameter that I'll denote by 1 over n. Well, in fact, the only operator product expansion coefficient that's of order 1 in this case is between 2 single trace operators, OI and OJ, and the double trace operator that's made from these 2 operators. So that's just the overlap between 2 single particle states in the bulk and a 2 particle state in the bulk. And the fact that these fields in the bulk are weakly coupled means that the dimension of this double trace operator OI-OJ is the same as the sum of the dimensions of the individual single trace operators, plus some corrections of order 1 over n squared coming from the interactions between these particles. Now, I discussed here quantum gravity theories on anti-de Sitter space, but as far as solutions to crossing are concerned, you can also just discuss a field theory on anti-de Sitter space, like just a phi to the 4th or phi cubed theory on anti-de Sitter space. Also in these theories, even though they're local field theories, you can just put in sources for them at the boundary and obtain correlation functions analogous to the ones of the ADA-CFT correspondence that automatically obey the crossing equations. And in some cases, you can even embed these field theories into the ADA-CFT correspondence as some decoupled sector of a full quantum gravity theory, and they would map to some decoupled sector in the d-dimensional CFT. So as I said, any bulk theory that you have, whether it's a field theory or a quantum gravity theory, gives you a solution to the crossing equation order by order in this coupling 1 over n. So at leading order in 1 over n, the only diagram that contributes to this 4-point function is this disconnected diagram. And if you do an operator product expansion of this, then the only operator in this diagram that appears in the crossing equation is the double trace operator made from two of these O's. That gives a diagram of order 1. If you look at this 4-point function at order 1 over n squared, then it gets contributions from these two types of diagrams. And here you can have single trace operators appearing in the OP that you can think of just by cutting this diagram, or also double trace operators appearing in the OP, and so on. Now, up to now, this expansion was analyzed just up to leading order in 1 over n squared, which means tree-level diagrams in the bulk, and 4-point functions of order 1 over n squared in the conformal field theory. And it turns out that in this order, the correspondence between solutions to crossing and bulk tree-level theories seems to be 1-to-1, at least when the conformal field theory obeys that it has a large gap to higher spin operators. So any solution to crossing seems to translate into a specific bulk theory at order 1 over n squared. And of course, well, the other direction is obvious, that any field theory in the bulk gives a solution to crossing up to order 1 over n squared. What we're trying to do is to take this one order higher, namely to consider loop diagrams in anti-de Sitter space and map them to solutions to crossing at order 1 over n to the 4th. So in a quantum field theory, once you know the tree-level action, then that determines also all of the loop amplitudes up to some finite number of local coupling constants that you can choose as renormalization conditions. And that's true even if you just have some effective field theory like supergravity, order by order in perturbation theory. The loop amplitudes are determined up to some finite number of coupling constants. So this is usually done in flat space, but the same should also be true in anti-de Sitter space. That once you know the tree-level action, the loop diagrams should also be determined. Unfortunately, computing these diagrams in anti-de Sitter space is much more complicated, and as far as I know, it was only done for the phi to the 4th theory, where Pinidonis and Fitzpatrick and Kaplan computed these diagrams, but it was not done even in simple cases like the phi cube theory. So for that reason, if we just start from finite diagrams in anti-de Sitter space, it's rather difficult to compute what the 4-point function should be at order 1 over n to the 4th. And again, even in well-known examples like n equals 4 super Young-Mills, it seems very difficult to use this method of Feynman diagrams to compute these 4-point functions at order 1 over n to the 4th, even though it is a well-defined question. So the question is, can we take a different approach and use this mapping between bulk theories and solutions to the crossing equation to compute, instead of using Feynman diagrams, to compute these things by using the crossing equation? Namely, can we take a solution to the crossing equation at order 1 over n squared, which again is just a tree-level bulk theory, and then use the crossing equation to go one order higher and to compute a solution at order 1 over n to the 4th. And well, there are two complementary motivations for this. One is to just compute the one-loop diagrams in the bulk by a method that may be simpler than the direct Feynman diagram approach, and of course to just do the 1 over n expansion of correlation functions. It would be nice if just knowing the order 1 over n squared terms of the expansion, you could also compute the higher order terms without adding any extra information. And preliminary results suggest that it is indeed possible to do this, again, up to the inevitable freedom that you have in changing the bulk coupling constants order by order in the perturbative expansion. More precisely, you can do it in some cases, namely you can do it if the only operators appearing in the OP expansion at order 1 over n to the 4th appeared already at order 1 over n squared, because otherwise you can always just add new operators here that you didn't have access to at order 1 over n squared. But in cases that you don't have any new operators appearing at order 1 over n to the 4th, then you can do this procedure. In some cases, you do have new double trace operators that appear. For instance, they can appear as intermediate states in this diagram. And then you have to add more information from the tree-level diagrams, for more tree-level diagrams that involve also these extra operators. But even in that case, just knowing the correlation functions coming from all of the tree-level diagrams seems to be enough to go to one higher order. And again, in some special cases, just knowing a specific 4-point function up to order 1 over n squared seems to be enough to go to order 1 over n to the 4th. So this means that, well, at least in simple theories like phi to the 4th in anti-de Sitter space or phi cubed, in those cases, the only operators that you have are this single operator dual to the scalar and its multi-trace generalizations. So in theories like that, you can use this method to compute the loop diagrams in anti-de Sitter space from the point of view of crossing, for some things it's easier to use a position space approach. For other things it's easier to use a melon space approach. And of course, the two approaches are supposed to give the same answers. Also, if you just look at the 5-dimensional n equals 8 supergravity on ADS5, which is a consistent truncation of type 2B string theory on ADS5 cross S5. So in that case, there's only one superconformal primary that appears in the spectrum of these bulk fields, which is just the lowest dimension 2 operator of the n equals 4 Cyprian-Mills theory. So also in that case, because you have just one operator appearing in the OPE, it's enough to know the correlation function at order 1 over n squared to go one order higher and to compute it at order 1 over n to the fourth. In a full theory like n equals 4 Cyprian-Mills theory, which is at strong coupling just dual to 10-dimensional supergravity on ADS5 cross S5, in that case you can have extra states appearing in this OPE, so say the OPE of O2 and O2, where O2 is the dimension 2 operator, can contain other double trace operators made from other operators. So in that case, to go one order higher, you need to know more, or at least it seems like you need to know additional 4-point functions. But still, if you know all of the 4-point functions at order 1 over n squared, and that certainly seems to be enough information just from the crossing equation to determine the correlation functions also at order 1 over n to the fourth. And again, this is up to some local bulk couplings that you cannot determine just from crossing. And in this case, well, in some cases you may be able to determine them from string theory. So string theory does tell us the precise coefficients in the effective action. And in some cases, we know how to compute them in string perturbation theory. So that gives extra information that you cannot see just from crossing. But up to these local terms that affect the 4-point functions only in very specific ways, you can obtain all the information just from the crossing equation. You could hope to go to higher loop orders and really, well, in some sense, solve the theory to all orders in 1 over n and compute higher loop diagrams in ADS. For that, it is clear that you do need additional information beyond just the value of the 4-point function at the leading order, because, for instance, you could have a 5-point coupling in the bulk that would give rise to a diagram like this, and you don't have any access to the value of that 5-point coupling if you just look at the 4-point functions at tree level. And that's related to the fact that the operator product expansion in these cases does not include just double trace operators, but it can also include triple trace operators. And again, when you go to higher and higher order, you can have operators that involve more traces that can also appear in the operator product expansion. So you do need more and more information as you go to higher orders in perturbation theory. But still, I mean, as one may expect from quantum field theory, it is enough to know all the correlation functions at the first non-trivial order in the 1 over n expansion, namely corresponding to tree-level diagrams in the bulk. Once you have that information, it looks like it should be possible just from the crossing equation to compute all the loop diagrams. And certainly for complicated diagrams like this one, it may well be easier to use crossing to compute them instead of using Feynman diagrams in the bulk. Of course, well, we haven't worked out all the details yet, so it remains to be seen whether this crossing method will be simpler or not than Feynman diagrams, but it certainly uses a completely orthogonal methods, so one can hope that it would be easier. So that's the end of the second topic that I wanted to discuss, and again, maybe we can save questions to the end. And the third topic that I want to discuss is disordered field theories, and again, as far as I could see, at least in Spires, that's a topic that Nati has not worked on yet. And again, I'm sure he'll correct me if this is wrong. And this is mostly based on work that I did with Zoal and with Shimon Yankelevich, and on work in progress with my student Vladimir Novlansky. So disordered theories appear naturally in condensed matter applications of quantum field theories, because in that case you often have inhomogeneities in your matter. It's not just homogeneous and isotropic. So you can have random inhomogeneities in your material. And in some cases, it turns out that they do affect also the continuum limit and the properties of the quantum field theories that you would use to describe these materials in the continuum limit. The simplest model that you can use to describe such inhomogeneities is to view these as some background fields for your quantum field theory that are coupling constants for that theory. And then to model your quantum field theory as a theory that has random coupling constants that are taken from some distribution for the possible coupling constants. So this is what's commonly known as quenched disorder. And then you assume that each sample of material that you analyze is taken out of this ensemble of random coupling constants, and you want to understand what's the typical behavior of some theory from this ensemble of different quantum field theories. So the types of things that we'll want to understand, well, that we can compute in these theories are this average over all the random coupling constants in your ensemble of of correlation functions or anything else that you want to compute in these quantum field theories. My motivation for looking at these theories does not come from condensed matter, but it's a general question about how the renormalization group works in the presence of this disorder. So these disorder averaged quantum field theories give us, in some sense, a new class of quantum field theories. They're not just standard local quantum field theories, but they still have some renormalization group flow where this disorder can be relevant, marginal, or irrelevant, and you can ask how these correlation functions depend on the scale. And the question is, how does the renormalization group work when you look at these disorder averaged correlation functions instead of standard correlation functions? And in particular, do you have some new types of fixed points that can emerge, or new types of phases of matter that appear in this context that do not appear in standard field theories where we just have constant coupling constants in space and time? So I'll make some simplifying assumptions for the discussion, most of which are not essential. So for simplicity, I'll assume that the disorder is just in the coupling to a single scalar operator. So we have some local operator O of x that has a coupling constant h, and I'll assume that the disorder in the material just manifests a random coupling constant h of x for that specific operator. And I'll assume that that coupling constant varies independently at every point in space-time, and it's just given by taken out of some Gaussian distribution at every point in space-time. The assumption that it varies independently at every point in space is, of course, valid if you're looking at distance scales that are much bigger than the typical scale of the variations in your material. So that's certainly true in the continuum limit of any condensed matter system. So I'll denote by an overline the average over all implementations of the disorder. So the disorder average. So I'll take the disorder average of this coupling constant to be 0, and the disorder average of a product of two coupling constants at different points to be proportional to a delta function with some coefficient c squared that characterizes the strength of the disorder. So in some sense, as Nadia likes to do, we're taking this coupling constant h of x and making it dynamical, except that here we're not adding a kinetic term for it. We're just taking it to come out of some Gaussian distribution. And there's also another difference from the usual case of dynamical background fields that I'll mention in a moment. Another simplification that I'll do is to look just at Euclidean quantum field theories, where the disorder varies independently at every point in Euclidean space. Those are relevant for analyzing second-order phase transitions in statistical mechanics in the presence of disorder. They're not relevant for another interesting case where you're analyzing, say, Lorentzian systems, where the disorder comes from, say, some impurities that make the coupling constants vary in space but still be constant in time. So that turns out to be a more complicated case that I won't discuss today. So the context today is just Euclidean quantum field theories with disorder coupling to a single scalar operator and taken from this Gaussian distribution. So the precise definition is that we'll take a disorder averaged correlation function to be a sum over all these different possible coupling constants with this Gaussian weight of the endpoint correlation function in the theory with a specific implementation of the disorder h of x, and that's computed from the path integral in the usual way by taking the path integral with these operators and dividing it by the path integral without these operators. Now this denominator here is very important because it means that this is not the same as just taking this coupling constant h and turning it into a background field, so just adding it to the action in this way. So this would give us this path integral, but again, the important thing is that we do want to normalize these partition functions separately for any implementation of this disorder, and that's why this really gives us a new class of theories that's not identical just to usual local quantum field theories, and one can hope that they would exhibit new phenomena. One interesting phenomenon that you can get directly from this definition is that in these disorder average theories, connected correlation functions behave rather differently from general correlation functions, which are not connected. So in the usual quantum field theories, once you know the connected correlation functions, you also don't know the disconnected ones, and vice versa. But in these theories, that's not true. For instance, if you look at the disorder average connected correlation functions, then that's given by taking the connected correlation functions in each implementation of the disorder and then averaging over them. But this is not the same as first computing the disorder average of O1 and then computing the disorder average of O2, it's important that here you first take this product and only then average over the disorder. So these two types of correlation functions behave in a rather different way in these theories. The connected correlation functions, well, because the connected correlation functions of each theory separately are generated by the derivatives of the log of the partition function, then you can also generate the disorder averaged connected functions by just taking this disordered free energy, that's the average of the log of z, over this Gaussian distribution. A general method to study these theories is what's called the replica trick. So you can take this log and rewrite it as the limit of the partition function z to the power n, where you take the derivative with respect to n at n equals 0. So that gives us this log. And the nice thing about this is that what's written here is just a standard quantum field theory, which is just n copies of your original quantum field theory, but all with the same coupling constant h of x. So the theory here is just a standard quantum field theory, but then you have to continue this to arbitrary real values of n and take the derivative with respect to n at n equals 0. That can be subtle in some cases, but at least if you're just doing a perturbation theory, even if you're doing some strongly coupled conformal perturbation theory, then this is certainly valid. So just taking the derivatives of this already gives you the connected disorder average correlation functions as objects in a standard field theory. And you could do the same also for the general disordered correlation functions. It turns out that from the point of view of this replica trick, the operators appearing in connected correlation functions arise in this replica picture from the sum over all the different replicas of that specific operator, while the operators appearing in general disordered correlation functions come in this replica description just from the operator O1 in a single replica, and that's related to the differences between the properties of these operators and correlation functions. The fact that we can get these theories as limits of standard quantum field theories means that you have, in some sense, the standard flow of the coupling constants, the standard beta functions, except for the case that in this description you do have this extra coupling constant c squared appearing here as the coefficient of a squared. So we have standard beta function equations, but with this extra coupling constant c squared. And therefore also you have standard RG flows that could end at a standard fixed point if c flows to 0. Then you end up at a standard fixed point, or if c flows to a non-zero value, then you would flow to some scale invariant point that's still disordered because it still has this parameter c squared in it. If you look at correlation functions, then you find that connected correlation functions obey just a standard renormalization group equation, which is just the first line here, again, because they arise just from correlation functions in this replica picture in standard field theories. However, if you look at the general correlation functions that are not connected, then they obey a different type of renormalization group equation where they also mix via some new anomalous dimension parameter with the connected correlation functions. So here we get a rather different type of renormalization group flow for these correlation functions. In particular, the connected correlation functions would generally flow to a standard behavior where they have some anomalous dimension, and the 2-point function would be 1 over x to the 2 delta. But if you plug that into this equation, you would find that the general correlation functions get an extra log in their behavior. And then for ed, so these flow to logarithmic conformal field theories, as Cardy found. And that's related to the fact that the operator in these two types of correlation functions in the replica picture come from two operators that are different but are degenerate. So that often leads to this logarithmic behavior. And that also means that you have in these theories new types of critical exponents relating to these new anomalous dimensions that appear in the renormalization group flow. So this was all a general analysis. One thing that we did is to perform explicit computations in these disorder theories when you have a large n limit, so that the theory becomes much more controllable, and then you can do computations either using field theory or using holographic duals. And we did many of these computations, and there we can explicitly exhibit these properties. It turns out, however, that in this case, the large n case is in some sense more complicated than finite n theories, because in the large n case you get extra degeneracies in these replica theory because between different double trace operators that don't appear in the generic case. And the thing that we're currently trying to understand is what happens in this more complicated case where you have a Lorentzian theory and the disorder doesn't depend on time. In this case, if you do this replica construction, you get a replica theory that's not local in time, so a priori we don't understand what the renormalization group flow looks like in these cases, and we're trying to see do they flow to new types of fixed points, and in particular, in a specific example, Hartnell and Santos found that these theories flow to fixed points that have a Lifshitz scaling with different scalings of space and time. And we're trying to see whether that behavior is generic or if there are other generic types of behavior. So to summarize, in this talk, I try to give some suggestions that Nati can work on in the next 60 years, obviously. But of course, probably Nati will not choose these directions, but will prefer to work on some completely different directions because like most other great physicists, Nati has often preferred to take the road less traveled by, and that has made all the difference. So happy birthday, Nati. And before the questions, let me just take advantage of this opportunity for an advertisement. So I'd like to invite all of you to the Strings 2017 conference that will take place in Tel Aviv at the end of June, and I hope to see you all there. So questions?
Thank you. We have many questions.
Hi, thank you. In regions of moduli space like M theory or F theory, if I'm working in flat space, when I try to use the perturbative bulk description of things, it only works in certain kinematic configurations. From what I heard you saying about the large N conformal bootstrap, you think that that won't be true in ADS space? That it'll be sort of the large N, I mean, the use of...
Yeah, no, sorry, I guess I wasn't clear. I mean, I was talking about large N, but taking operators whose dimension stays fixed in the large N limit, and if that's what you mean. So these techniques should certainly be useful just if you have a big gap in the large N limit between some class of operators and some other class of operators, well, either in the large N limit or in some other limit like strong coupling where you have a separation to the string scale. So these methods are only useful in cases like that where you have a large separation of scales, which in the ADS bulk maps to having some effective field theory description where higher derivative coupling constants are suppressed compared to the lower derivative coupling constants so that you have some approximate locality. So of course, if you don't have any approximate locality in the bulk, then all of these methods are useless, and you have, well, once you have a known local theory in the bulk, of course, you can't use all these Feynman diagram expansions.
Was slightly different,
okay.
I think. It's a question of whether there are boundary kinematic configurations for which this expansion breaks down.
No, that
I think you're saying no.
Yeah, well, okay, there may again be order of limits issues if you want to take angular momentum that's of order n or something, but certainly if you keep everything in your correlation function fixed while taking your cutoff to be very large, then I think it works for all kinematics.
Okay, thank you.
As far as I know.
I only need one. I have a question about part one of the talk, and maybe I completely misunderstood, but these S-folds that generalize orientifold planes, are they sources of Ramon-Ramon fields?
Yeah, that's a very good question. Let's see if I know the answer to that. I would certainly expect that they are. I mean, just even in the k equals 2 case, the orientifolds are sources for that.
Right.
So I think they are, but of course we don't have a perturbative string theory description for them, and we only control them at large n while these effects are order 1.
But
so I'm not sure if I know how to compute that, but I certainly expect that to be true.
You can say things about that source by using anomaly cancellation, and so I'm wondering if I think that should be done, because for the orientifold planes, it's actually a very interesting formula. It's roughly speaking the square root of the Hertzbruch genus up to some subtle powers of 2.
Yeah, that's right. But can you see in that context the discrete torsion effects on the orientifolds? I'm not, well, anyway, it should certainly be possible to do that.
The answer to that is yes. The
Okay,
literature
good.
is rather confused, but the answer is yes.
Okay, good. So that should certainly be possible, and it's a very interesting thing to do.
Does k equals 2 give n equals 3, or only k bigger than 2?
No, k equals 2 always gives n equals 4. That's just a standard orientifold 3-plane, and they're... So those theories are well known. Yeah, sorry, I mean, yeah, I didn't write it here, but k equals 2 is certainly the standard case where you have n equals 4 theories with gauge groups SON and SPN.
There are other peculiar superconformal algebras. Some of them, even the number of supercharges is a power of 2. and they have not yet been explored.
That's true, yes.
Is anything
I did
known
not
about
mean to
them?
imply otherwise. Certainly, n equals 1, 3 theories in 2 dimensions and so on.
Even two.
Yeah, that's right. So I certainly did not mean to imply otherwise.
So I guess one could think of this as a quotient by S duality, right?
That's right.
And so people in the past, I think Comron and Ed had found that when you do S duality, you get some changes in the back, and you get some terms proportional to the curvature, and to the Weyl tensor, and to the Euler class. Do you expect those terms to vanish for these special values of tau? Or maybe they don't matter?
Are these terms related to the source to the Riemann fields that Greg was mentioning?
I have no idea.
They're probably related by supersymmetry to that somehow, but yeah, I'm not sure. Naively, I would expect that anything that's there for orientifolds would also be present from these theories, because orientifolds are just a special case of this construction. And I wouldn't expect, there may be extra terms that are allowed by n equals 3 supersymmetry, but would not be allowed by n equals 4 supersymmetry. So again, generically, I would expect anything that's allowed to be present, but I don't think anybody's analyzed what are all the terms that are allowed consistent with n equals 3 supersymmetry. I mean, certainly, if you're talking now in the full string theory, then n equals 3 supergravity is more restricted even as a weakly coupled theory than n equals 4 supergravity. So it's possible that there would be some new coupling constants there, and again, that's an interesting open question.
Okay, let's thank Ofer again and go for coffee.